Welcome to topic 3.4, molarity. In this video, we will begin our discussion of molarity. In nature, we find mixtures of substances to be much more common than pure substances. The air we breathe is a mixture of multiple different substances. Steel is a mixture, and sugar dissolved in coffee is a mixture. Back in chapter 1, we learned about two different types of mixtures, heterogeneous and homogeneous mixtures. Most of the foods we eat are heterogeneous mixtures, where each sample or bite of food will have a little different ratio or percentage of each of the components or ingredients. So, for example, in pizza, your first bite might have more cheese than the second bite, whereas the second bite might have more sauce or pepperoni. Or take, for example, trail mix. If you take one spoonful of trail mix, it might have more M&Ms, and then the next spoonful might have less M&Ms but more raisins or nuts. A homogeneous mixture has all the components evenly mixed throughout the mixture. Each sample of the substance will be the same as the next sample. The amounts of each component in the mixture will determine the properties of that mixture. So, for example, the amount of oxygen in the atmosphere of a planet or moon is one of the key factors in determining if the planet can sustain life. Too much oxygen or too little oxygen in the atmosphere makes it impossible for life to survive. The amount of carbon in steel determines how strong the steel is. The amount of sugar in coffee determines how sweet the coffee is. And the amount of certain drugs and medications determines how it will affect the disease. And here's the funny that fits with this topic. Homogeneous mixtures are also called solutions. Even solid or gaseous homogeneous mixtures are called solutions. In our previous examples, air is a gaseous solution, and steel is an example of a solid solution. You should write down these definitions on your notes. I don't usually ask direct definition questions on the quiz or test, but you do need to know what each of these are in order to understand how to do the problems. Concentration is the relative amount of a given solution component. So we can find the concentration of sugar in coffee. Solvent is the component that has the higher concentration and it does the dissolving. So in the coffee example, the coffee/water is the one that is dissolving the sugar, and it is the solvent. If the solvent is water, where most of the time it is, but if it is, then it is an aqueous solution. Aqua is the Latin word for water. So you can think of these as water solutions, and it's where water is the solvent. And let's look at the definitions of these next four. The solute is the component that is present in lower concentrations. It's the one being dissolved. So in the sugar coffee example, the sugar is the solute. Dilute and concentrated are two relative terms. Dilute means you have a lower concentration of the solute, and concentrated means you have a higher concentration of the solute. There's no number that tells you whether it's dilute or concentrated. It's just relative to where it was before or compared to another solution. Dilute is also a verb. You can dilute a solution by adding more solvent. So, for example, if you have too much sugar in your coffee and it doesn't taste good, because it would be extremely difficult to take the sugar out, instead, we would add more coffee and then we're diluting the concentration of sugar, even though we're not changing the amount of sugar that's actually in your coffee. You now have a dilute concentration, though, of the sugar. These last definitions here for solution, solvent, and solute are very important. These three are the ones that you need to know the difference between and the definitions of each. So again, the solvent is usually the water, and it's the one doing the dissolving. The solute is what is dissolved in the water and being dissolved. And the solution is both the solvent and the solute added up together. Molarity is the unit for concentration that we are going to learn how to calculate. Molarity is equal to moles of solute over liters of the solution. Remember, solute is the component that is being dissolved, and the solution is the total amount, both the solute and the solvent. These units are very important. The solute must be in units of moles. They cannot be in units of grams. And the solution must be in units of liters. It cannot be in any other volume unit. The abbreviation for molarity is a capital M. Whenever it's typed, it's often italicsed. Remember that a lowercase m equals meters, and this is very different than the capital M, molarity. This equation is on your periodic table, so let's go look at it. If you look on the miscellaneous equations box, we have molarity. Molarity, capital M, is equal to moles of solute over liters of solution. Notice there's one that is very, very similar called molality, and we're not doing that one right now. .0 is read as 3 molar or 3 molarity. It is very important for chemical solutions to be labeled on their container not only with what chemical it is, but also the concentration. Let's try this first practice problem. A 350 milliliter soft drink sample contains 0.133 moles of sucrose, which is table sugar. What is the molar concentration of sucrose in the beverage? We are asked for molarity, moles over liters. The sugar, or the sucrose, is the solute. It is what's being dissolved. So we have 0.133 moles of sugar in the numerator. The volume of the solution is the 355 milliliters, but we need to convert this into liters. We're going to put milliliters on bottom and the liters on top. Using the metric system equations box on the back of your periodic table, we have 10 to the negative 3 liters is equal to 1 milliliter. This becomes our denominator in our equation. When you multiply 0.133 moles when you divide these numbers, the 0.133 by 0.355, we get 0.375. And the units is moles per liter. You could write these units as just a capital M. Either way works. Let's rearrange this molarity equation to solve for the other variables. In problems, you might be given 2 of these variables and asked to solve for the other one. So in the original equation, molarity is equal to moles divided by liters. But if we were given the molarity and the liters and we needed to solve for moles, then we would want to multiply liters on both sides of the equation, and we'd end up with this. So then we can multiply molarity times liters and get moles. Now in the next equation, if we wanted to solve for liters, we can take this equation that we just rearranged and divide molarity on both sides of the equation. And we're left with this. Moles divided by molarity, which is the concentration, is going to be equal to the volume of the sample that you have. And here's the answers typed out. Let's try this next problem. How much sugar in moles is contained in a small sip, or 10 milliliters, of the soft drink from the example 3.14, which is just the example we did recently? So in this problem, we want to rearrange our original equation. So molarity is equal to moles per liter. And it says how much sugar in moles. That gives us the clue that we want to solve for moles. So we're going to take molarity times liters, and that's going to be equal to moles. The molarity from the previous problem was calculated as 0.375, and its units are moles per liter. The volume in this problem is 10 milliliters. Of course, we need to convert that to liters. 1 milliliter is equal to 10 to the negative 3 liters. So we have 0.010 liters. 0.010 liters. Notice that in these problem here, the way I have it written out with the units for molarity, we have liters in the denominator can cancel with the liters in the numerator of the volume. And now, when we solve this problem, we get 0.00375. And this is how much sugar is in just one sip, or 10 milliliters of the soft drink. Here's the problem all worked out. Try to solve this problem on your own before moving on to see the answer. Distilled white vinegar is a solution of acetic acid, which has this compound here, and it's in water. A 0.5 liter vinegar solution contains 25.2 grams of acetic acid. What is the concentration of the acetic acid solution in units of molarity? We want to solve this equation. We want moles divided by liters. The liters of solution are given right here in the problem, so our denominator for this equation is 0.5 liters. We know that the acetic acid is the solute. It is what is being dissolved, and we need moles of solute. However, we are given 25.2 grams of acetic acid. So let's convert grams to moles. The acetic acid can be written as C2H4O2. It has all the same compounds, or all the same elements. When you find the molar mass of 2 carbons, 4 hydrogens, and 2 oxygens, we get 60.052 grams per 1 mole. We can cancel the grams, and we're left with moles. So we need to divide 25.2 divided by the 60.052, and we get 0.4196 moles. Don't round this number very much because you can see we have 3 significant figures here and 3 significant figures here. So we want to have at least 3 digits in our answer, so let's use at least 3 or more in all of the calculations. So that number of moles, 0.4196, is going to be the numerator of our equation. When we divide this, we get 0.839 molarity. And you can write these units as 0.839 molarity or 0.839 moles per liter. It means the same thing. And there's all of the calculations typed out. Now you can complete the first 6 problems in problem set 3.4. Let's go ahead and look at those in the practice set. So here's problem set 3.4. We have problem 1, and then 2 and 3, and 4, 5, and 6. So it's almost 2 pages worth of problems. We're going to learn dilutions and molarity of ions in the next video.